Hi, everyone. Welcome to the video on hypothesis testing. So far, we've talked about the more theoretical underpinnings of research, the kind of big picture things like critiques and types of studies and probability and survey design. And now we're moving on to more applied quantitative research. So if you remember way back when we did critiques, one of the items on the worksheet that you guys used to sort of structure your critiques was whether they used appropriate methods and analyses. And that was the one that we couldn't really address yet. So now that's what we're going to be focusing on, how to answer that question. The way we do that is through hypothesis testing. We talked about hypotheses in research questions, and back when we talked about research questions, and any study that has a hypothesis is going to end up doing a hypothesis test. All that really means is we're going to use inferential statistics on sample data to evaluate whether our hypotheses could apply to a population. And details of a hypothesis test will change from one situation for another, but the general process is going to remain consistent. It's really based on the idea of the distribution of sample means, that sampling distribution that we talked about last week. And that's essentially what hypothesis testing is. What we're going to be doing is we are going to take what we know about a population and we're going to take a sample from it, and using what we know about the sampling distribution, we're going to say whether our sample is likely to have come from that population. So in an experimental context, and I'm just using experiments here as an example, the same general principles are going to apply whether we're using a predictive study, an explanatory study, or an experimental study. But experimental is easiest to understand, so I'm just going to start there just to explain the logic of it. So the idea is, before there's a treatment, before you administer the intervention or the drug, in the case of a drug test, you know certain things about the population before you administer those things. And then after you administer them, you take a sample, you give them this intervention, and then you test them and you say, is this the same as the population that we knew beforehand? And that's fundamentally what all hypothesis testing is doing. It's just saying, we know what you're like before. Are you the same after? How likely is it that you were the same as this population that we already knew about? And that's fundamentally what all hypothesis tests are about. And it doesn't matter whether we're doing experimental, predictive, or explanatory studies. So if I was interested in whether there's a relationship between education level and IQ, for example, the known population would be all of Canada, where we know the mu for IQ is 100. And what we want to know is, when we break that down by different education levels or different numbers of years of education, is that population the same as Canada in general? So our second half, our right side of the screen, would be the sample that we're pulling, say, people who have masters, and then comparing the IQ and saying, is this the same as Canada in general, or is it different? So that would be not a experiment, that would be a predictive or an explanatory variable. But what we would be doing is essentially comparing that to the population we know about. It's the same general principles. In fact, the only kind of study for which this doesn't apply is descriptive studies. And I bet you can guess why. If you guess that they don't use inferential statistics, then you're right. This is fundamentally an inferential statistical procedure. Now, that said, if your descriptive study does, for whatever reason, use inferential statistics, then yeah, you're right back here. Anything that you're using inferential statistics, this is fundamentally what you're doing. So for the purposes of illustration, for the rest of this video, I'm going to use the same example. And it's going to be a general example of, let's say we have a specific question that we might have in mind in a specific area of interest. In this case, I'm going to say it is, do students whose teachers have a master's degree have a higher IQ than the general population? And then what we're going to talk about today is how we would go about finding the answer to that. Now, just as a quick side note, if anyone was wondering, the reason I keep using IQ as an example is that it's a kind of test that everyone has heard of, and that is population normed, which means that we know what the population looks like, which you'll remember from probability makes a lot of these statistics easier. So this is sort of like the simplest version of it. I haven't suddenly developed a random love for IQ tests. We're using this because it's the simplest version, because it has it has a known population. We already know what that is. So in order to test this, we're going to do 5 steps, these 5 steps of hypothesis testing. First, we're going to specify our problem, then we're going to take and test a sample, then we're going to set up a null and alternative hypotheses, and then we're going to use the sampling distribution to calculate the probability of observing a mean at least as large as our sample mean, and then on that basis, we're going to decide to reject or fail to reject our null hypothesis. And then here's what each of those 5 steps are going to look like based on the example that we just talked about. It's okay if all this sort of sounds like nonsense right now. It's meant to, or it's not meant to, but it's using a lot of jargon. And so we're going to go through it one at a time, and then hopefully this jargon will start to make sense by the time we get to the end of this video, as opposed to now at the beginning. So step one is identifying your research hypothesis or your area of interest. So you start with an idea. You want to test something. You have a theory as to how it's going to turn out, and you want to figure out if you're right. The hypotheses and research questions that we talked about before are actually here in step one. This part we've already done. We've already thought about what we want our topic to be. We've thought about potential research questions, and we've thought about how we could phrase those as hypotheses. So we've already spent a whole week talking about this, and we're feeling pretty good about it. Yeah, yes. In this case, for our research question, which remember is, do students whose teachers have a master's degree have a higher IQ than typical children? We can pretty easily convert that into a hypothesis just by making it a statement. So with step one covered, we're going to move on to step two, which fortunately we also pretty much have covered. It's doing the actual work of the study. So we're going to identify the constructs, operationalize them into measures, and then we're going to collect a sample and test that sample on all the measures we've identified. So if we took, say, a random sample, in the case of our example, we're going to take a random sample of 25 students whose teachers have a Master's of Education degree, and we're going to give them each an IQ test. Once we calculate all that up, we found that the mean IQ of our sample of 25 to be 106. Now this is where we take the big leap from what we've been previously discussing and what we're going to be discussing for the rest of term. So once we've established based on what we think what will happen, so once we've done step one, and then we've gone out and collected our data, that's step two, now we have to figure out whether our findings are meaningful or not. Is 106 actually greater than 100? Is that a real difference, or is that a statistical artifact? Is that sampling error? What's going on here? So the way we do that is we want to know if our sample of students with Masters of Education teachers or teachers who have Masters of Education was in fact drawn from a population with a mean of 100. So are students with Masters of Education teachers or teachers with Masters of Education the same as typical students? And the way we're going to phrase that numerically is we want to know whether 25 people with an average of 106 is the same as a population mean of 100. So in other words, what we're asking is whether this sample is the same as the population that we know something about. We are asking whether we could get a sample of kids in general that would score an average of 106 IQ purely by chance. How likely is it that we would get that sample if we were really dealing with a population where the mean is 100? Now I realize that the confusing thing here, or one of the many confusing things probably, is that last week when we talked about probability, we talked about how important it is that the sample was like your population, that sample reflected that population. And now we're saying that we actually don't want to show that sample. We actually don't want it to be the same as the population. We want to say that students whose teachers have a Master's of Education actually is higher. It doesn't make sense for that population to have a mean of 100. This is from a whole other population where the mean is 106. And that sounds weird because we just spent so much time saying that we wanted to make sure our students were like the population. And yeah, that's exactly what we're doing. It's supposed to be confusing like that. We want to be able to say that this group that had an experimental treatment or was accounting for this explanatory variable of Masters of Education teachers or included some other predictor variable, whatever group that we have specifically selected out, we want to say that they're different. And we want to be able to say that we can say why they're different. They're different because of this Masters of Education. They're not different for reasons of ethnicity, or they're not different for reasons of gender, or they're not different for whatever other reason. All those nuisance variables that we talked about several weeks ago, we want it to not be that. And so that's why it was so important for our population and our sample to match, so that when we go ahead and do those comparisons, we can say that the comparison to the population is because of this one variable that we're interested in, whether that's a predictor variable, an experimental test, or a explanatory variable, whatever. So in order to figure out whether this actually works, whether 106 it does equal 100, we have to go through a scientific method to calculate the probability of how likely it is that our sample would come up with 106 if in fact the world said the mean was 100. So that brings us to step 3, which is that we need to set up a null hypothesis. A null hypothesis states that there is no change, no difference, or no relationship. In other words, that the population from which our sample is drawn is the same as the population we know. In the context of an experiment, for example, the null hypothesis would predict that the independent variable would have no effect on the dependent variable. In the context of an explanatory variable, we'd say that there's no effect of that variable. And in the context of a predictive study, we'd say that there's no predictive relationship between the two variables. For our particular example that we're talking about today, our null hypothesis would be that there is no difference in IQ for students whose teachers have a Master's of Education than other students. So why do we do this? Why do we set something up to knock it down? Well, it comes from Fisher, who is a philosopher of hypothesis testing. And essentially, he argued that you can never prove something right. You can only ever prove it wrong. So, for example, if you see 3,000 cows with one head, it doesn't prove the hypothesis that all cows have one head. But if you find one cow with two heads, it would prove that hypothesis wrong. So you can never fully eliminate something. You can only ever prove things wrong. You can't ever prove something right. Now, some people really have argued with this, especially people who really don't like positivism. This is the real sticking point for them. But for our purposes, it works pretty well, so we're going to stick with it. So we're going to set up a null hypothesis for our study, and the way we express that statistically is that population 1 is not equal to population 2. Or you could also say population 1 minus population 2 equals 0, which means the exact same thing. So for our example, again, the null hypothesis is going to be that 106 minus 100 equals 0, or that 100 equals 106. And now we're going to go ahead and try and disprove that. Now, the inverse of that, we're also going to have a scientific or alternative hypothesis, which we might call H1 instead of H0. And what it's going to say is exactly what we think is going to happen, so that there will be a change, a difference, or a relationship for the general population. In the context of an experiment, the scientific or alternative hypothesis is going to predict that the independent variable will have an effect on the dependent variable. In a predictive study, it'll be that one variable will have a predictive relationship with the other, etc., etc., etc. For our example, the alternative hypothesis was going to predict that students whose teachers have a Master's of Education will have different IQs. So in this case, as you can see, the alternative hypothesis is really almost exactly the same as the research hypothesis. The only difference for ours in particular is that it's not directional. So we're not saying that students whose teachers have a Master's of Education are going to have higher IQs. That's what we're saying in the research hypothesis, but that's not what we're saying here in the alternative hypothesis. Here we're just saying that it's different. Now, you can have an alternative hypothesis that is directional, but in education research, that's pretty uncommon. Usually we stick to either the null hypothesis is that there'll be no difference, and the alternative hypothesis is that there will be a difference. And the way we write that statistically, you can probably already intuit from what we just talked about with the null hypothesis. We can say mu1 minus mu2 does not equal 0, or that mu1 does not equal mu2. In our particular example, that would be 106 minus 100 does not equal 0, or that 106 does not equal 100. Okay, so now that we've set up a null hypothesis, we can move on to step 4, which is calculations. Now, there are a lot of different ways to do calculations, and we're going to spend a lot of time discussing different statistical tests. But all statistical tests, without fail, are variations on one equation, and that is signal over noise. The signal is the difference between our sample and the null hypothesis population. That's the bit we're really interested in. The noise is our natural error in selecting a sample. To clarify a bit, let's go back to our old friend, the sampling distribution. This is the sampling distribution we made last week, but as you all hopefully remember, that almost all sampling distributions look the same with only the numbers changed. So if we think of this as the sampling distribution for the overall population, and the mean was 100, there could be two possible reasons that we draw a sample with a mean of 106. Either A, we just happen to get a really wonky sample. That's totally possible. As you can see, the point of having a curve means you could just draw a sample that was weird. Or B, the other option is that our sample doesn't actually reflect this sampling distribution. It reflects some unknown sampling distribution, presumably from a different population with a mean of 106. Option B, we can't test directly. But you may remember from last week, the one thing we can do is calculate the probability of getting any particular sample mean from a population by using the sampling distribution. So what statistical tests do is they put our mean somewhere on the curve of the sampling distribution. They don't give us a probability quite yet, that's the next step, but what they do is they tell us where along this curve our particular sample is likely to be. And the way they do that is by putting the difference between our sample mean and the population mean over the average distance between any sample mean and any population mean. So all tests are basically the same and they're all working towards the same goal, but which version you use is going to depend on a few different pieces of information. First, what type of variables you have and what information you have available. So we're going to go through some of these over the term, not all of them, but for the purposes of today, we only have to figure out which one is going to work best for our example. And that's the key point of the calculation step, honestly. The actual math usually is done by a computer. Picking the test is really the hard part. For our example, our dependent variable, or it's actually a criterion variable for us, is continuous. It's IQ. And it's an interval, continuous interval variable. So we're going to use the continuous one. And then our independent or predictor variable is whether those students have whether those students' teachers have a master's of education, and that's categorical. Either you have a master's of education or you don't. So we'll pick categorical there. And then we have to think about what information we have available, because we do different calculations based on what pieces of information we have. In this case, because the dependent variable is IQ, and we know a lot about IQ, we know the population mean and we know the population standard deviation, and that's just because that's how IQ works. The mean of IQ is always 100 and the standard deviation is always 15 within the population. So based on that, we know, because we know that, we know what we're going to do is called a Z-test. So from there, once we've decided that we can do a Z-test, we're going to go ahead and do the calculations of that. This is the formula for a Z-test. And all the Z-test really does is take our means and give us back what that means in terms of standard deviations. I'm sorry, the word mean is showing up too much there. But what that means is, what I'm saying is, within the sampling distribution, how many standard deviations from the population mean is our sample mean? That's what I'm trying to say. And Z is simple enough that we can calculate it by hand. And actually, this one is simple enough that you might even be able to do it in your head. So let's take a minute now and do that. Pause here if you need to. And hopefully, you guys got 106 minus 100 for the top part, and then 15 over root 25 for the bottom part, and that's going to work out to 2.00. So now that we know that Z equals 2, what do we do with that? So Z equals 2, that means our sample is 2 standard deviations away from the population mean. But is that a lot? In order to decide whether that distance is meaningful rather than just something that could happen by chance, we need to do some additional thinking. And that leads us to step 5, which is the decision. In order to make sense of the numbers, we need to turn our score, in this case the Z score, into a probability value. And we talked about this a little bit last week, so maybe you can guess where this is going. We're going to examine the sampling distribution that could be obtained if the null hypothesis was true. And within that sampling distribution, we're going to categorize all the potential means into 2 categories. Those that are likely to be obtained if the null hypothesis is true, and those that are unlikely to be obtained if the null hypothesis is true. And once we figure out where our Z score falls, whether it's likely to be true or unlikely to be true, we can make a decision about whether our sample is meaningful and whether this is a meaningful difference. So to figure out which of those categories our sample falls into, we need to do 4 things, sorry. First, we're going to need our score, which we already have, is we know is Z equals 2, and that's going to pinpoint for us where along the sampling distribution our mean is going to be. And then we're going to need our alpha, the tail, and sometimes we're going to need degrees of freedom, and I'm going to talk about each of those things more in a minute. So this is our hypothetical sampling distribution for IQ for samples of n equals 25 of the null hypothesis. And you remember our overall goal here is to see whether our mean is likely to have come from the same population as the null hypothesis. And we want to be able to say no. We want to be able to say that no, it's unlikely that this came from our null hypothesis population. Now, you remember from previous weeks that sample means that are closer to the null hypothesis population mean are more likely. We know that 68% of means are likely to be within one standard deviation of the population mean. And you remember last week when we talked about probability, I mentioned that in addition to knowing how likely it is to be within the first standard deviation, we can calculate the probability of being at any point under the curve. And that's essentially what we're looking to do for making a decision here. We have our z-score, which is going to tell us where on the curve we are. And then what we're going to do is we're going to convert that to how likely it is to be at that point under the curve. If it's unlikely that we came from this population, so the parts of this curve here that are marked in red, we would say that those are unlikely means to get. It's unlikely to get those means if this is the accurate picture. If the null hypothesis is true, if this sample came from this population, it would be very unlikely to get a mean this size. But we don't just randomly color in parts of the sampling distribution in red. We need to pick a specific probability value at which to say, yes, this is unlikely enough for us to be able to say that we wouldn't get this by chance, that it's extremely unlikely. The level we set that is known as the level of significance, or the alpha level, or alpha, for the hypothesis test. And what alpha basically does is it sets the level that we're comfortable saying that this sample probably comes from a different population. In social sciences, including education, it's normally set at 0.05. Sometimes you'll see people play around with it and have an alpha of 0.01 or 0.1, but like 99.9% of the time it's 0.05. So there's always a chance we're going to be wrong, is what alpha is saying. If we say, you know what, I'm saying that if there's a less than 5% chance that this sample mean came from this population, then I'm fine saying that it came from a different population. That means that we're saying I'm okay with being wrong about 5% of the time. And that's why it's so important that we set an alpha level that we're comfortable with. So for our example, we're going to choose 0.05 or 5%, and that's because that is the standard in social sciences research. If for whatever reason we're not comfortable with that, we can always make it narrower or broader. But it's so rare that you would see one beyond 0.05 that you typically have to have a really good reason for choosing something different. Another thing we have to decide before we decide whether our sample mean is in the rare zone or not is whether we're going to be looking at both sides of a distribution or one side. And if it's one side, then which side? So if we look at one side, that's called a one-tailed test. If we look at both sides, it's called two-tailed. And the decision of which one to use is going to depend a lot on your hypotheses. If you have a specific hypothesis that only goes in one direction, so if we really thought that students whose teachers have a master's of education have higher IQs than typical students, we could do a one-tailed test because we only want to know about children who fall into this one extreme category. The two-tailed test is for times when we think it could go either way. We may have theoretical reasons to think that students whose teachers have a master's of education may be different from typical kids, but we may think it could be either higher or lower. Now, even though we already know our mean is 106, and so it would basically be impossible for it to be lower, we generally have to make these decisions ahead of time, whether you're going to do a one-tailed or two-tailed test. And so most of the time we choose two-tailed. And if you remember back a few minutes ago when we set the null hypothesis, we specifically set it as a non-directional alternative hypothesis. So for our example, we're going to choose two-tailed. Now, all that really means when we say we're choosing a two-tailed test, it means that in order for our alpha to be 0.05 or 5%, we have to say that in each tail, it's 0.025 or 2.5%. So the total red region accounts for 5% of scores, not 5% at either end. And then the final piece of information that we need sometimes is called the degrees of freedom. Now, in the example that we've been using, we actually don't need the degrees of freedom. We could go ahead and make a decision now before we talk about degrees of freedom. But because the broader goal here is to have a general understanding of hypothesis testing, let's take a minute and talk about degrees of freedom. And some parts of this are going to make more sense in the coming weeks because we are going to use degrees of freedom a lot. We're just not going to use it right now. And the reason we don't need it right now is because we know the population standard deviation, which means that we can calculate the standard error relatively easily. You'll remember that the central limit theorem gives us a really clear way of calculating the standard error if we know the population standard deviation. But a lot of times we don't know the population standard deviation. In fact, most of the time we don't know that. So we have to use an estimate to get to standard error. And if we're basing our standard error on an estimate of the population standard deviation, there's some flexibility there. There's a chance that we're wrong, and we have to be able to account for that. Now, when we get to those situations, I'll explain the different ways of making that estimate and different ways of doing that, so don't worry about that now. But the important thing is that we're going to base our estimate on our sample data. We're going to use our sample to make an estimate of what the population standard deviation might be. And so because we're using our sample, that means our hypothetical sampling distribution is going to be limited by our sample size. And so we have to say that our sample variability is restricted, and we have to say by how much. So let me use sort of an analogy for you that hopefully will help this a little bit. So an analogy for degrees of freedom, I'm going to talk about food for a little bit. So it's not 100% accurate in terms of an analogy. It's just a way to give you sort of a general idea of what degrees of freedom mean. It's Zootopia in that way. The metaphor is pretty solid, but it'll fall apart if you really, really try and think about it. Okay, but let's imagine a scenario in which you're in a cafeteria and they offer a selection of desserts. And it's just a sample from a larger population of many different kinds of desserts that could be offered. But on this particular day, they have 5 desserts. And to keep this simple, they only have 1 of each dessert and only 5 people, only 5 customers. And all these people work their way down the cafeteria line, and they get to the dessert section, and they have to decide what they're going to eat for dessert. And in this scenario, how much choice does everybody have? How much are individuals free to vary? And so let's consider the scenario. The first person gets in line gets to select from 5 desserts and chooses the apple pie. The second person gets to select from the 4 remaining desserts and chooses the chocolate cake. The third person gets to select from the 3 remaining desserts that are left, and they choose a sundae. The fourth person takes fruit out of the last 2, and then the last person has to take the last dessert, which is stale cookies. Now, each of these observations is free to vary. That is, until we get to the very last person who has to settle for the stale cookies, everybody else gets at least some choice. And that's basically what degrees of freedom is. So n-1 scores are free to vary. Just as n-1 people can choose the dessert of their choice, n-1 of our individual scores in our sample are free to vary in the cafeteria, are free to vary in our sample. Back in numbers land, this is sort of what we mean. So if we took, say, here we have 2 different samples of 4 scores each, and we know that the mean of this population is 100, then each sample that we take, the first 3 can be anything within the range that would be possible for that particular test. But then the last score, in order to make that mu equal 100, that last score has to be a particular score. And here we can see for each one, it works out differently what that last number has to be. So it's not a constant score that has to be part of each one, but it's an inflexible score that is going to have to be a certain thing within our sample. So there's always at least one number that doesn't have the luxury of choice. It has to be a certain thing. So we usually say our degrees of freedom equals n-1, just like in the cafeteria. It's our sample size minus 1, because every number in our sample can again theoretically vary except for 1, and that would, in order for that mean to make sense. Now, I know that's sort of confusing, and we'll talk more about it next week and in the coming weeks, but the important thing to think about here is that the degrees of freedom are necessary when we're discussing the significance of the test, and calculating the standard deviation of a sample is the important thing to take away here. And the reason it is because our variability is limited within a sample. So then going back to our step 5, which is what we're actually talking about, in order to make our decision, for our example, our data doesn't actually need degrees of freedom. And that's because we have the population SD, so we can calculate standard error and go ahead and make the decision without accounting for the fact that we're going to have limited variability. Because theoretically, we don't have limited variability. We know the population standard deviation. So what we need is the alpha, and that we're doing a 2-tailed test, and of course we're going to need our probability, which we know is 2. So once we've made those choices, which we have, we're going to go ahead and find a table that matches on the probability for each z-score of getting, of the chances of finding that sample according to a certain z. In order to do that, we use what's called a z-table. Now, in reality, no one uses tables anymore. You're going to, when I say you, I mean generally, if you were doing quantitative research, you would use a statistical program that would just spit the probability back at you without a problem. But because we chose not to use statistical programs, we didn't want to buy statistical programs, we're going to use tables for our study. So we're going very old school, but it's sometimes helpful in tables in terms of thinking about um, the theoretical understanding of how these computer programs work. So the way we are going to do it from here is this is a Z table, and I'll post the same one for you guys to use when you're working on your lab assignments. But the rows on the left-hand side are going to show Z to 1 decimal place, and then the columns along the top are going to show the second decimal place. For our study, you can see that you remember that the Z-score we came up with was 2.00. So we're going to look in the rows, we look down to 2.0, and then in the columns, we're going to look at 0.00 because we know our score is 2.00. And that's going to give us a probability of 0.0288. So that's our probability of finding a score at least as big as 106. So remember, it's going to give us the probability of getting our score, a score at least as big as this score. So there's always a probability that could be higher, but it's going to say the chances of being this much or higher is 0.0228 or 2.3%. So once we have our p-value, which is what that is, that probability value is called a p-value, we can decide what to do with our results. And we have two choices. If we reject the null hypothesis, we're saying it's wrong and that our sample comes from a different population. If we fail to reject, we're saying that we can't disprove the null hypothesis and that it may be true. Now, remember, as we talked about before, we never prove something right. So we never accept the null hypothesis, or we never prove the null hypothesis. We only reject it or fail to reject it. So the probability of getting a mean of 106 from the null hypothesis population is about 2.3%. So what would we do? Would we reject that, or would we fail to reject that? So we did a two-tailed test with an alpha of 0.05, which means that at either end, we want our probability to be less than 2.5% in order to reject our null hypothesis. And what our table just told us is that our data is, so it looks like we're just inside the line to reject the null hypothesis. Our p-value, remember, we found was 2.3%. That's just under 2.5%, and we can go ahead and reject that null hypothesis. It's in that red area that we talked about being rejection area. So based on that, we'd say that students whose teachers have a Master's of Education are significantly different from typically developing students. So going back to our 5 steps here, we can see that we've actually completed a null hypothesis. We've completed an entire hypothesis test. We came up with a research hypothesis that children whose teachers have a master's degree have a higher IQ than other children. We obtained a sample of children whose teachers have a Master's of Education degree, and then we gave them an IQ test. We then set up a null hypothesis that children with Master's of Education degree teachers do not differ from typical children in terms of IQ, and then we also added on an alternative hypothesis that maybe they are different. And then given the sampling distribution, we calculated the probability of observing a mean at least as large as our sample mean. What we actually did is we figured out that Z equals 2.00, and then we used the Z table to convert that into a probability and found out that there's about a 2.3% chance that we would get that mean if the null hypothesis were true. And then from there, we were able to decide, well, 2.3 is lower than 2.5, which is what it would need to be in order to match on with our alpha level for a two-tailed test. And we decided to reject the null hypothesis. And that's all there is to it. All the tests that we have going on from here on out are going to follow roughly the same format. And we'll talk about them in more specificity, and steps 4 and 5 are going to vary. But by and large, this is what hypothesis testing is. But there are a couple more pieces that we need to talk about before we can fully move on from talking about hypothesis testing broadly and start getting into the more nitty-gritty of it. And the first is errors. And there are 2 ways that you can make an error in terms of hypothesis testing. And they're called, coincidentally, type 1 and type 2 errors. Type 1 error is the error of rejecting the null hypothesis when the null hypothesis is actually true. And that happens when we say that the null hypothesis is wrong and when it's not really. So in a typical research situation, a type 1 error would be that a researcher concludes that a treatment has an effect when in fact it doesn't. So if we were doing an intervention, we would do an intervention and we get a significant finding and we say, this intervention makes a difference, it helps kids learn, but it turns out it doesn't help kids learn. It was just by chance that we got that. Now, fortunately, the way we set up hypothesis tests, they're really geared towards guarding specifically against this. It's structured to control and minimize the risk of making this type of mistake. And the way we do that, of course, is because we structured the entire thing about saying that it's super unlikely we would get this finding. And in fact, we decided what super unlikely meant. Remember, in the decision step, we decided to set our alpha at 0.05 or 5%, and that meant that we are comfortable saying that we are going to be wrong 5% of the time. But that means that we're making a type 1 error 5% of the time. Type 1 errors is, the chance of making a type 1 error is the exact same as alpha. It's always 0.05 or 5%. Type 2 errors are a little bit different. They happen when you fail to reject a null hypothesis, even though the null hypothesis is false. So in a typical research situation, a type 2 error would be something like a hypothesis test has failed to detect a real treatment effect. So we did our study, but we decided we couldn't reject a null hypothesis. The intervention didn't seem like it made a difference, and we say, oh, this intervention doesn't work. But it turns out it did work. It's just for whatever reason we didn't find a significant effect. Now, maybe you were tipped off there by my saying for whatever reason, in that type 2 errors are a lot harder to measure. We don't have that same exact probability value for type 2 errors that we do for type 1 errors. So we refer to it symbolically as beta, but whereas alpha, we can say we know there's a 5% chance we're going to make alpha. Beta, it has more of a formula, and there's a lot of different factors that go into what our chances are of making a type 1 error. So we just typically call it beta. Or a type 2 error, because our hypothesis testing is really geared so much towards making sure we don't make a type 1 error, an alpha error, that it's actually not uncommon to make type 2 errors. We've essentially decided we'd prefer to have type 2 errors than type 1 errors. And here's a little chart that'll hopefully make those errors clearer. So on the rows, we have what the experimenter does, and then the columns are the actual situation in the actual world. So if we reject the null hypothesis, but the null hypothesis is actually true, that's a type 1 error. If we reject the null hypothesis and the null hypothesis is false, then we made the right choice. Great job, us. If we fail to reject the null hypothesis and the null hypothesis is true, then excellent, another great decision we have made. But if we fail to reject the null hypothesis and the null hypothesis is actually false, the effect does exist, then we'll have made a type 2 error or a beta error. And then finally, another important caveat to hypothesis testing is this idea of effect size. So the p-value that we pull out, the probability, only tells us the chances that we would observe a mean that big in the null hypothesis population. So if the null hypothesis are true, the chances that we would observe a mean this size is what the p-value tells us. So a p-value of 0.05 and a p-value of 0.01 don't tell us anything about the strength of the effect. There's no such thing as being very significant. A certain mean can be more or less likely to come from a null hypothesis population, but that's not the same thing as having a big impact or a big effect. So in addition to p, we also have to consider how big the effect is. And that is what effect size does. It's a measure of the strength between two variables. And effect size calculations differ based on the type of data we have. They basically, like the different statistical tests we do, they go hand in hand with that. So every different statistical test will probably have a different effect size that we would use with it. And so for the analyses we're going to do in this course, we're typically going to be looking at effect sizes in terms of Pearson's R or Cohen's D. And I'll talk about each of those and what they mean when we talk about the tests that they're associated with. But the important thing to know now is that effect size is a way to measure the strength of a relationship and that it's different from P. So that brings us to the end of roughly outlining hypothesis testing. Each of these steps, as I said, are going to be roughly the same for each study we're going to do. These 5 steps are going to be basically the same. What's going to change is the content of them based on our particular topic and our particular hypothesis. So our problem is going to be different. The way we obtain and test the sample is going to be different. Our null hypothesis is going to be dependent on what we're interested in. It's going to be dependent on our topic. The choice of what statistical tests we're going to do in step 4 are going to vary based on steps 1 and 2 in terms of how we acquire our sample and what our variables look like. And then step 5 is going to vary based on the calculations we use in step 4. So each of these are going to vary, but overall these 5 steps are going to be the steps that we are going to use pretty much for the rest of the course.